All right, so this marks the beginning of chapter 20, which is on nuclear chemistry. Nuclear chemistry uses almost nothing that we have learned so far in 2 semesters of chemistry, so it's literally like starting over. That doesn't mean it's difficult, it's just different. Okay, so a couple things we need to review is you guys may remember way back in chapter 2 of last semester that we talked about this format. Let me try to label a few things here. So this is if you have an individual atom, if you have carbon, this would be a C. It's the elemental symbol. Okay. Z is the atomic number, basically how many protons it's got. Since we're talking about the nucleus, we start caring about protons and neutrons a whole lot more all of a sudden. And this A value is the mass number. And it's equal to the number of protons plus the number of neutrons. Remember that protons weigh 1 and neutrons weigh 1. So it's going to be nice whole numbers for both of these. Okay? So, when we talk about nuclear reactions, what we're talking about is we almost genuinely don't care how many electrons there are, which seems weird because we spent 19 straight chapters focusing on electrons. We care about protons and neutrons, and whether protons and neutrons are gained or lost or changed or whatever, okay? So anytime we have nuclear reactions, the way this works is when we balance nuclear reactions, we don't care how many of each element are on each side, like the reactants and products. What we care about is that the sum of the atomic numbers, basically the Z values, and the sum of the mass numbers must be equal for the reactant and product side. One of the things we're going to see is that the identity of the atom is going to change a lot whenever you decrease the number of atoms or whenever you decrease the number of protons anywhere in the process. So up to this point, we've always had the same number of each type of atom on each side, the reactant and product side, and that's what we called balanced. Now, we're not going to have the same atoms on each side. What we have is the same number of neutrons and protons. Okay. We will see this in context. It's not as hard as it sounds, actually. It's pretty straightforward. So, there are 5 different types of radiation. We're going to start talking about those. They're all variations of radioactive decay. Oh yeah, I guess a quick thing before we get too far. I guess I should point at the one that's legible. N-U-C-L-E-A-R, nuclear. You can say nuclear, that's fine. Nuclear is not a word. There's only one U. There is no possible way that the second half of this word makes the Euler sound. It's nuclear. Please try your best. All right, sorry. So, end rant, I guess. Radioactive decay. There's 5 different options. The first one that we're going to talk about are called alpha particles. Probably should have started at the beginning of a new page, but whatever. Okay, so alpha particles get abbreviated as an alpha, the Greek letter alpha. Okay. And what happens is this is when a nucleus, which is, the neutrons and the protons, this is when it loses the equivalent of it basically loses 2 protons and 2 neutrons. Can't write legibly, sorry. So it's 2 protons plus 2 neutrons. And it all kind of happens at once. So like the 2 protons and 2 neutrons are stuck together. They are a thing. Well, if you had two, if the bottom number was 2 because you had 2 protons and you add these together to get the top number, well, that would be helium, right? It's element 2, its mass is 4. This is a helium. It also doesn't have any electrons, so it's going to have a 2+ charge. So when we say an alpha particle, we literally mean a helium particle being shot out of a nucleus. Again, this feels a little weird. It's very different, but it's not difficult. Because it has a positive charge, it is deflected by magnetic fields. Not a huge deal, but sometimes if you have radiation, it's one of the ways you can distinguish which type of radiation is a problem, is happening at that moment. All right, I'm gonna continue alpha particles. I'm not done with them yet. Okay, so as far as alpha particles, a couple things to keep track of. So I guess I'll write this up here. So for alphas, they have low penetrating power, which we've never had to worry about anything like that before. What we mean is, typically when we deal with radiation, we are trying to avoid getting exposed to radiation. So we want to know, how do we stop it? Okay. Well, it turns out that alpha particles are stopped really, really easily. Basically, if you have a piece of paper and you just like hold it between you and the radiation source, it's enough to stop the alpha particles from going through. Your skin is good enough. Okay. So has a very low penetrating power. So it's stopped by paper or skin. Like, you don't need much to stop it. The only time that it's really dangerous is if you inhale it or if you eat it. If something is emitting alpha particles inside of your body, then it's really, really, really dangerous, and your risk of cancer goes up really, really quickly. So it's super scary if eaten or breathed or inhaled. Okay, so let's look at an example of how these reactions work. So, if I told you that uranium-238, uranium element 92, we're going to start dealing with the bottom of the periodic table. We've kind of ignored this for 19 chapters. Something like uranium-238 is the most common isotope. Its average weight is 238.02, whatever. Okay. If I asked you to write the balanced equation for uranium-238 undergoing an alpha particle emission, this is what we would expect. It's an emission, so it's going to be a product. It's emitting an alpha particle, so it's going to be one of the products. So I'm just going to go ahead and write, this is the alpha particle. I'm going to go ahead and write it over here. Okay, and what we said before is when we balance this, we need the sum of the atomic numbers to be the same on both sides. We need the sum of the mass numbers to be the same on both sides. So on this side, the top numbers add up to 238 and the bottom numbers add up to 92. We need the same thing over here. Well, 90 plus 90, or 90 plus 2 gives us 92. So 90 is going to be the bottom number. And 234 plus 4 will give us 238. Well, 90, we need to figure out what element that is. Okay, element 90 is thorium. This is a pretty typical looking nuclear reaction because we don't have any of the same elements on each side, but the sum of the atomic numbers and the sum of the mass numbers adds up to the same thing on each side, the reactant and product side. Okay? You guys don't have a great way of knowing that this would be an alpha particle emitter. I would have to tell you, but as long as you can write the balanced equation, that's all I really need out of you right now. All right, that's 1 of 5. Let's do the other ones. They're going to kind of go faster as we go. The second one is a beta particle emission. So, beta. Okay. It turns out that neutrons can, sometimes just fall apart. And it turns out that they are the equivalent of a proton and an electron added together. Because electrons have essentially no mass, but they have a negative charge. So they're like an antiproton. So this side 1 plus 0 equals 1, and 1 minus 1 equals 0. It turns out that this is a beta particle. So this is what's being emitted from the nucleus during a beta particle reaction. Okay, it should have a negative charge. It's essentially an electron. So even though there's no electrons in the nucleus, it is possible that an electron can form when a neutron becomes a proton. This is weird stuff that we've never had to think about before, but that's okay. Because it has a negative charge, we saw a minute ago that things that have positive charges are deflected by magnetic fields. They're basically pushed away. Things that have negative charges are attracted to magnetic fields. They have a pretty high penetrating power. They're more likely to actually like get through your clothes and actually do some damage. Okay. The example most textbooks use is like if you had a 3 millimeter thick piece of aluminum foil, so if you had like that heavy duty aluminum foil, that would be enough to stop it. This also, I guess, lends to the conspiracy theory idea that, you know, you wear your tinfoil hat to stop the government from reading your thoughts. Apparently they're assuming that beta particles are part of the process, I guess, I don't know. Now, although they do have a higher penetrating power, they're significantly less dangerous than alpha particles. So if you do actually get exposed to them, it tends to not do a lot of damage. Okay, so let's look at an example. It turns out that this thorium-234 that we just created in this as a product here is a pretty common beta particle emitter. So let's look at what that does. So, same idea, it's being emitted, so it's one of the products, and we essentially just have an electron as our product. Well, in order for this side to add up to 90, this would have to be 91, because 91 minus 1 adds up to 90, and this number doesn't change, because it doesn't have any mass. So if you look at the periodic table, which we haven't really used in a while, we basically took one step to the right. So when you have an alpha particle emission, you're taking 2 steps to the left and losing a mass of 4. When you emit a beta particle, you take 1 step to the right, is essentially one way to keep track of this. I usually just add up the numbers and make sure they work and find it on the periodic table. Okay, kind of weird. Let's keep going. Okay, there's three more left. And let's see how this goes. So the next one is kind of weird. These are called gamma rays. This is a Greek gamma, assuming that I'm, even remotely good at writing Greek letters. These are essentially just very high energy photons. So literally it's just light, it's just pure energy. Okay, and they have a very, very high penetrating power. Like literally nothing you can do will stop it. Like literally, like if one of them hits Australia and goes through the bottom of the planet, it could still get through and hit you. There's really nothing you can do to stop this one, so don't worry about it. Okay. When we talked about electrons, when we talked about like s and p and d orbitals and the 1s2, like electron configurations, we said that when we talked about the Bohr's hydrogen atom, we said that electrons going from one energy state and then falling back down emits light. This is the same concept, but it turns out that the nucleus has its own ridiculous organization. And it turns out what happens is a proton or a neutron gets promoted to a higher energy state and then it falls back down. Okay, exact same thing that we saw with electrons. We are not going to learn about the horrifying organization of what's going on in there, partly because we don't know. But we do know that that's what's happening. But it's the exact same concept, but because it's partly based on mass, and protons and neutrons are, 1,800 times heavier than an electron, the energy output is going to be, 1,800 times bigger. So, let me try to write some of that down. These are emitted when some sort of energetic proton or neutron falls to a lower energy state. So it's exactly the same concept we saw with electrons last semester. Not a big deal. Turns out that this can literally happen to pretty much anything, just like electrons can be promoted. So I'm going to pick that same thorium-234 that we just saw. If I can write things legibly, sorry. And literally, these might be your favorite ones, not because they're meaningful or anything, but they're really easy to keep track of. Essentially, it goes from an energetic state, which we show with an asterisk, and it falls to a normal state. None of the numbers change. These ones are pretty easy. For what it's worth, there's the idea that when you have a black hole, what's happening is as the black hole starts absorbing all the mass around it, everything sort of spirals and swirls into that center, okay? And what happens is, as everything gets crushed, E equals mc squared, I'm oversimplifying here, but all that mass gets converted to energy, and most of the energy can't leave the black hole. Gamma rays are about the only thing that have enough energy to do so. So it turns out that there's just a fountain of gamma rays coming out above and below the disk of spiraling, being destroyed matter that exists in a black hole. Gamma rays are one of the easiest ways to actually detect a black hole. All right, keep moving. This video is going to get too long if I don't. Two more. This is a positron emission. And this is essentially a positive version of an electron, so a positive beta particle. It is literally antimatter. It's the antimatter version of an electron. So in other words, it has no mass and it behaves exactly like an electron except that it has a positive charge. Okay. Here's the problem. Antimatter and regular matter destroy each other and create lots and lots of energy as soon as they even come into contact. So its penetrating power is pretty limited because it immediately will destroy any electrons that it hits, and electrons are everywhere. The problem is that when they hit, they release a lot of energy by destroying each other, E equals mc squared and such, and it starts releasing gamma rays. So there's another source of gamma rays. So basically, an electron plus a positron destroys all the matter involved, and what you end up releasing is 2 gamma rays. I don't know why it's 2, but it is. Okay. This is kind of what happens when a proton turns into a neutron. And sorry, that's a positive one. A positron is released. So it looks just like the electron, except it's positive, not negative. You're real clever with your namings. It's a positive electron, so a positron. This technically can happen to pretty much anything. It's just a proton turning into a neutron. This isn't like, really heavy nuclear, like radioactive elements. It's pretty much happens to it could happen to anything. It's pretty uncommon, but it could technically happen. So, it can happen to something like aluminum. Okay. And so what happens is, this positron gets emitted. It says emission, so it's going to be on the product side. Well, to make the numbers work out, this would have to be a 12. The mass doesn't change, so that's still, 26. I don't know why I wrote 23. Element 12 is magnesium. So this is a magnesium. Not too bad yet, right? Okay, last one, then we'll call it a day. Well, call this video over at least. All right, so the last one, this is gonna sound super nerdy, but is my favorite of the bunch. Not because it really matters compared to the others, it's because it's something that people never ask. It's a question that people never ask me, even though it seems super obvious. So way back when I told you about protons and electrons, I said protons are positive, electrons are negative. I said positive repels positive, and negative repels negative, but positive attracts negative. Opposites attract. Nobody ever asks, like, okay, we've got all these positive the positive protons in the nucleus, and we have all these negative electrons around the center. Why don't the electrons get attracted and crash in there? Well, it turns out that occasionally they do, and that's what this one is, electron capture. It's what happens when a low-level electron falls into the nucleus. Okay. Essentially what's happening is an electron interacts with a proton because negative, positive, and it's kind of the opposite of what we saw earlier. It forms a neutron. Well, as we said in the last semester and earlier in this video, if you have electrons in high energy and they fall down, light is released, energy is released, okay? Well, if you have a bunch of electrons and you remove the bottom one, all of them will fall. They'll all fall down to fill the gap at the bottom. It's kind of like if, you have a stack of oranges at the store and you pull the bottom, if you pull something off the bottom and the whole stack falls down, that's what happens here. You pull the bottom electron out and all of them fall. So what happens is it turns out that X-rays are emitted in this process. So X-rays are emitted as all the electrons fall to lower levels. Okay. As far as you guys are concerned, essentially you just write an electron on the left side and make the numbers balance out. So if we had something like, I don't know, iodine. Okay. An electron capture means that it is being added to the nucleus. It's falling into the nucleus. So it's actually the only one where it's on the left side. But it's literally the same thing as a beta particle. But instead of being emitted from the nucleus, it's being absorbed into the nucleus. In terms of the numbers, 53 minus 1 is 52. And this is 0, so this stays there. And we get element 52, which is tellurium. Okay. I will need you to know all 5 of these and how the reactions are going to work. Like, you'll need to memorize that. Sorry. All right. Thank you.